Now in today's video lecture, we would be going through rate law equation for those batch reactors in which volume is not constant. Till our previous video lecture, we have considered those batch reactors that have constant volume, right? So now let's look at the rate law equation for those batch reactors with variable volume, right? That is, volume of the batch reactor changes with position, right? Normally we seldom face such batch reactors where volume changes, right, or batch reactors with variable volume, because mostly these are steel cylinders with constant volume, right? So let's look at the rate law equation. Rate law equation is rate constant CA CB, right? Concentration of reactant A, concentration of reactant B, this would be negative, right? Now we want concentration. What we were doing till previous equations for rate laws, we were deriving concentration in terms of conversion x, right? So now if you get concentration in terms of conversion x, you will substitute the expression for concentration here to get rate in terms of conversion, right? Now we will be following a little different procedure here to find concentration as a function of conversion for batch reactors or flow reactors with variable volume, right? We would be using here equation of state, right, to find volume as a function of conversion, right? So wherever you have variable volume, right, for batch reactors or flow reactors, you would be finding volume, you would be finding expression for volume as a function of conversion, right? So we would be finding volume as a function of conversion, right? So to find volume, we know one thing, that concentration, because anyhow we need individual concentrations, right? To get concentration, for example, for A, we have number of moles of A divided by volume, right? So once you have volume, what you have to do is, in order to get expression for this concentration, you will find it using this definition of concentration, which is moles per unit volume. So once you have volume as a function of conversion x, you will substitute the equation in this expression for concentration, right, to get concentration as a function of conversion, right? So once you have concentration as a function of conversion, you will substitute in this equation to get rate in terms of conversion, right? So let's quickly look into it, right? Because individual concentrations, right, can be determined by using volume for a batch system, right? Once you get volume for a batch system, you can find individual concentrations, right, by substituting volume in the expression for concentration, right? So volume, right, individual volume you can get individual volume as a function of conversion, right, using equation of state, like I said before. So equation of state is PV is equals to Z NTRT, right? This is the equation of state, right? Using this equation of state, we will find volume or volumetric volume for a batch reactor or volumetric flow rate for a flow system, right, from this equation, right? If for batch reactors, we would be finding this volume V, right, and for volumetric flow reactor it would be nu, right? Volumetric flow rate is denoted by nu. So first, in this video lecture, we would be deriving volume as a function of conversion for batch systems, right? And using this concentration expression, we will find concentration in terms of x, then we will substitute it over here like we were doing before, right? So this is equation of state, right, say at any time t, at any time right? So initially at time t is equals to 0, equation of state would be this. R is gas constant, it would be constant. P is pressure, V is volume, R is gas constant, right? Z is compressibility factor, right? Which tells you the deviation of real gas from the ideal gas, right? You have done this in gas laws in school chemistry, if you remember, right? So what we will do, we will be doing is we will be dividing these two equations, this by this, V upon V0. This is a simple derivation, right? For initial it would be NT0, right? At time t is equals to 0, and this is for a gaseous reaction, right? This is for gas phase reaction. Let's say it's this reaction. For this reaction, right? So Z upon Z0, NT upon NT0, T upon T0, right? So therefore it will change to V is equals to, just rearranging this equation, P0 upon P Z upon Z0 NT upon NT0 T upon T0. Right? Now, what we want is, we want volume as a function of conversion, right? This is what we want. We want to express volume as a function of conversion. And if you know from our previous, when we were building stoichiometric table, NT represents number of moles, right, remaining after a reaction, after certain conversion, the number of moles remaining, and NT0 represents number of moles of reactants, total number of moles of reactants and products initially fed into the reactor, right? And this represents total number of moles of reactants and products at time t, right, which is this NT, right, which is this NT at any time t. NT0 is initially the total number of moles initially fed. So the relation between NT and NT0 can be derived using stoichiometric table, right? So we would be building stoichiometric table like we were doing it for other rate law equations, right? So this is your stoichiometric table. We were deriving this for a gaseous reaction, for this gas phase reaction, right? Gas phase reaction, and this is the stoichiometric table that we need to build. So this is NT0, initial number of moles fed into the reactor. This is conversion. This represents how much reaction has occurred, and this represents the total number of moles at any time t, right? So this is the expression that you will get, right? We did this in the previous video lecture, so you can check out this for the previous lecture for rate laws and stoichiometry that we have done before, if you have any doubts related to the stoichiometric table. So this is the expression that we will now use further, right? From this relation we can find, if you divide this entire equation by NT0, right, NT upon NT0, right, we will divide it like this, NT upon NT0 is equals to, when you have divided both the sides with NT0, right, 1 plus delta NA0 upon NT0 dot X conversion, right? And what is this delta? This delta represents this quantity, this expression, right, for the moles of reactants and products, right? We have derived it from this addition, right? So delta would be D upon A plus C upon A minus B upon A minus 1. This would be, you take 1 upon A common, D plus C minus B plus A. Right, this is for this gaseous reaction, right? This represents your increase, this represents change in the total number of moles, right? D plus C, this is for products, D plus C, A plus B, right? So this is your change in the number of moles between reactants and products. Change in the number of moles, right? A. And this is your A represents number of moles of A reacted. If you look at this equation, number of moles of A reacted. So this is your change in the number of moles divided by moles of A reacted, right? Now let's just solve this further. This equation, because from this equation only we would be deriving volume in terms of conversion x, right? So this equation would be Nt upon Nt0 is equals to 1 plus, we would be taking this quantity delta Na0 upon Nt0 as epsilon, right? Epsilon x, right? Where epsilon is equals to delta Na0 upon Nt0. This is simple derivation, simple mathematics that we are doing from the beginning of this chapter, right? So in a way epsilon represents this, delta is this quantity, right? So it would be D upon A plus C upon A minus B upon A minus 1. Right? And if you look at this, what does this represent? This is your Na0. Na0 is initial number of moles of A fed. Nt0 represents the total number of moles. This is the total number of moles. So Na0 upon Nt0. If you just recall, you have done this in stoichiometry in your school chemistry. This is your mole fraction of A. Na0 upon Nt0, that is moles of A out of total number of moles, is your mole fraction of A. Similarly, if it is Nb0 upon Nt0, this is mole fraction of B. Similarly, Nc0 upon Nt0 is mole fraction of C, right? So we would be denoting Na0 upon Nt0 by Ya0, right? We will denote mole fraction by Ya0, which represents the mole fraction of A. Right, this is your Ya0, delta Ya0, epsilon, right? So therefore epsilon is equals to Ya0 dot delta. This is the relation between epsilon, this is epsilon, right? And Ya0 is your mole fraction of A. Right, now we will further solve epsilon, right? We will solve it for epsilon. If you just look at this equation only, we will solve this equation further. We'll bring this one here. It will become Nt minus Nt0 upon Nt0, right? Is equals to epsilon. We'll bring this x down. This is what it will become, right? Now we'll consider this equation for complete conversion. For complete conversion, right? That is x is equals to 1, right? Why x is equals to 1 at complete conversion? X is equals to 1 and your NT would be total number of moles. This total number of moles at x is equals to 1 would be NTF, final total number of moles, right? And x is equals to, if you just recall, moles of A reacted divided by total number of moles of A fed into the reactor, right? Total moles fed into the reactor, right? So at complete conversion, when we say complete conversion, that means total number of moles will react, because X conversion represents how much of reactant have reacted. So at complete conversion, this total moles fed into the reactor, right, will react. So moles of A reacted would be equal to the total number of moles that you have fed into the reactor, right? So at that point, both these quantities will become equal, so x would be equal to 1. So that is why at complete conversion x is equals to 1 and nt is equals to ntf, right? So epsilon would be ntf minus nt0 divided by nt0, right? This is the expression for epsilon. So now if you look at this ntf and nt0, this represents change in the total number of moles for complete conversion, right? Change in the total number of moles for complete conversion, because this represents this NT, right? And NTF is when x is equals to 1. That means x is equals to 1 means when total number of moles of A that you have fed into the reactor have reacted, right? So at that point, total number of moles will become NTF, right? We are taking A as the basis of conversion, right? So, and we know that A is the limiting reagent. When we are talking that for complete conversion of A, that means A is the limiting reagent that have completely reacted in the reaction, right? So this expression is clear, right? For complete conversion, at complete conversion, when this reaction will get complete, total number of moles remaining would be NTF, right? And initial number of moles that you have taken is NT0, right? So after complete reaction, initially you have taken NT0 moles, right? After complete reaction, NTF number of moles have left. When we say converge for complete conversion, that is when the reaction has completed, right? So we have taken it with reference to A, right? For example, if this is your A, right? If we are taking it in reference to A, when NTA, right, would be equal to the total number of moles that you have fed in the reaction, right? If A is your limiting reagent, that means reaction have completed, right? Because none of moles of A is left, right? So this represents the total number of change in the number of moles, right, for complete conversion. Initially you have taken this number of moles, final number of moles is your NTF, right? So this is your change in the number of moles, change in the number of moles divided by, this is your initial number of moles, right? Change in the number of moles, then you have initial number of moles. If all the species in the generalized equation are in gas phase, right, we can substitute equation, the one that we have derived, NT upon NT0 1 plus epsilon x, right, in this expression, right? So let's just do it. We will substitute NT upon NT0 here in this equation, T upon T0 1 plus epsilon x, right? This is what the equation will change to, right? Now in this equation we will take compressibility factor as it will not change, right? Because compressibility factor depends on temperature and pressure, right? So in gas phase, this is a gas phase reaction that we are considering. So in this gas phase reaction, temperature and pressure are such that the compressibility factor will not change significantly, right, during the course of reaction, right? So here the temperature and pressure will not change during reaction, right? Therefore Z upon Z0, both Z and Z0 are same because compressibility factor is not changing, so this is equal to 1, right? So here V will become V0 P upon P0, right? This has become 1 T upon T0 1 plus epsilon x, right? This is the expression for volume, right? Volume of gas for a variable volume batch reaction, right? This is the expression for variable volume of variable volume batch reaction. This is the expression for variable volume batch reaction, right? Because we are doing it for batch reactor, so this variable volume represents for batch reaction. So V is the volume at any time t, right, from this equation, and V0 is volume when at initial stage, right, when initially the reactants and products have fed into the reactor, when reactants were fed into the reactor, right? So using this expression from stoichiometric table, we will derive a relation between volume and conversion x, right? Now you have this expression for volume in terms of conversion x. You will substitute this expression here in this equation to get individual concentrations, right? For example, Cb would be equal to Nb upon V, right? So in this expression you will put this. So what you will get is conversion in terms of x. If you substitute this V here in these equations, so you will get individual concentrations Ca and Cb. So once you substitute Ca and Cb here, you will get rate in terms of conversion x, right? So I hope this is clear. This is just a simple derivation, right? Just remember two things here, that we have used equation of state, right? We would be using equation of state, right, to derive volume in terms of conversion x, right? So term volume for this is for any gaseous reaction. For any gaseous reaction, the term volume can be obtained from equation of state, right? And since you need to relate volume and conversion x, so conversion x, right, this x, conversion x can be taken from this expression, right? Because if you look at this equation, if you divide this equation, you have this moles of A at any time t and initial number of total moles, right? Total moles at any time t, total moles initially. So these two terms are related using this equation, right? These two terms can be related using this equation. So you will further solve this equation to get this value of epsilon, right? And epsilon is this, right? And this Na0, you will get this Na0 upon Nt0, right, from this equation. And Na0 upon Nt0 is moles of A out of total number of moles, which is your mole fraction. So this epsilon changes to this, right? Now we'll further solve this equation, right, for complete conversion x is equals to 1. For complete conversion at x is equals to 1, total number of moles at any time T would be NTF, right? This NTF is this NT, total number of moles at when X is equals to 1, right? So what you get is change in the total number of moles upon initial number of moles, right? So this is your volume, right? This is your expression for volume, right, in terms of conversion X. So you will substitute it in this expression for concentration to get concentration in terms of conversion X, and we'll substitute it here in rate law equation, right? So I hope this is clear. After this video lecture, we would be deriving the similar expression for rate law for flow systems, right, where we will consider variable volumetric, we would be considering volumetric flow rate, right, volumetric rate, right. And here we have considered temperature and pressure such that compressibility factor has not changed. So both these are equal, that is why we have taken this equal to 1, right. So I hope all this is clear. Thanks.